All right, now physics people are going to have to go in just a couple minutes. So before you take off, let me talk to you a little bit about what the requirements are for this course in terms of supporting stuff. There's no textbook for the course. I'm not sure if you've been checking the price of textbooks lately, but it's ridiculous. The average price for a geology textbook now is about $180, which is just not worth it. For this class, I do have some requirements for you. You don't absolutely need a laptop computer. Since all of you should have had one for mineralogy, you might as well bring it in. It's useful. You are, however, going to need one of these. Hardcover notebook. This is what you're going to be using for field work as well as for your lab work. Don't go out and get one of the Rights in the Rain ones, because I don't like working in the rain anyway. What you want is one that's got blank pages on the inside, because ultimately what you're going to be doing is using this for recording, as I said, field notes, but also for doing your thin section lab assignments. For example, stuff like this. Okay, so we're not doing this until we get into about week 6 or so you have plenty of time in which to do that. But get this as soon as you can. And the reason why you want to get one that's about like this, a field notebook really should be something that's easy to get to easily. So back pocket is a great place for a field notebook. I used to, when I was young and naive, I used to buy the belt with all the leather things on it, including the leather attachments. But you know what? It's nerdy, and they immediately know that you're a newbie geologist. So you don't have to worry about these leather or metal holders for your hammer. The best thing for a hammer are those little metal clip things. Put through a belt loop, put your hammer through it. It's great, and it saves on weight. Trust me on this. You're going to need a Swiss Army knife or something that's got capabilities of scraping down an outcrop. Okay, so a small Swiss Army knife with a bottle opener, because the one thing that really annoys me is if I'm at Moscow Landing and I don't have my corkscrew with me, somebody better have one. Okay, so I need that. A hammer is, believe it or not, is not that important for sedimentology, because most of the stuff we're dealing with is really kind of soft. Although at St. Stephen's Quarry it gets pretty hard in some places. Far better is a scraping tool, and I found the ultimate thing. You know what this is? This is a Japanese hoe. And it's absolutely perfect. Look at the inclination on this. You scrape down an outcrop, it's brilliant. Cost me $35, but boy, it's brilliant. If you want to get high tech, something like this is the way to go. Okay, this is a clipboard, and you just open it up, put pages on the inside. I added this on the outside, pens and stuff like that, and rulers. Every once in a while you do need to take maps out with you, although it's getting less important to be taking maps with you in the field, because these days everybody has GPSs and all. You're not going to need a GPS for this class. You're not going to need any of the high-tech stuff. That's basically it. Oh, and also, don't forget, you should all have a quality hand lens, okay, because you are going to need that as well. And if I were you, I'd put it on a line so that you can put it around your neck, because that again looks uber cool, but it's also useful when it's available to you. Okay, so you are going to need this. You will not need it until we do Scarborough School as our field trip. Okay, you're not going to need this in Moscow at the Municipal Park trip this Thursday. Okay?
Am I going to need to find my long lost transit?
Sure. Do you need it? No, but you should find it. I mean, it probably cost you a few bucks and also. Yeah. I mean, if you got a GPS, bring it. Bring a digital camera with you, because whenever you, let's face it, whenever you go in the field, you're going to see something cool, take a picture of it. All right? But stuff like that's not going to be absolutely necessary, and someone will have a camera somewhere. Moscow Landing, however, that's different, because then you are going to want to take some photographs to augment your report, etc. I would bring a camera to Municipal Park too, because you might want to photograph your study area once you get it done.
These field trips are going to be camping?
The only one you're going to be camping at is Moscow Landing. Although many people have found St. Stephen's Quarry to be such a neat place, they bring their tent, camp there overnight as well. If you do that, you're on your own in terms of the camping fees and all. But how many of you have been to St. Stephen's Quarry before? You know, it's pretty. They got a big body of water in there. Some people bring kayaks and float around and all sorts of things and all. So once you're there, you're going to like it. So feel free to camp if you want to. Okay? And by the way, those trips, St. Stephen's Quarry and Moscow Landing, are open to anybody who wants to come along. Scarborough School and Municipal Park, who wants to go to Scarborough School, are not really open to anybody else. I do have travel permission forms if anybody is interested in bringing a friend along for the other trips, however. I think you've probably been all told we no longer have to do travel approval forms for trips that are required for the course. So you guys don't have to fill out anything, but if you want to bring a friend along who's not in this class, they will have to do it for Moscow Landing or for St. Stephen's Quarry. And we'll probably open up those trips to the local geology people here as well, too. Okay, let's get started with part 2 of today's double lecture. Now, as I said, this would normally be done on a Thursday, but I wanted to get caught up a little bit, and this gives us plenty of time on Thursday to do the municipal park walkthrough. We're going to talk a little bit about grain size and descriptive parameters. The first project you're going to be doing in this class is a grain size project. You need to know how grain size works and what it's all about. So here's our agenda. We're going to be talking about basic sediment grain size. We're going to be introducing or reintroducing ternary plots, since you've all seen them previously, but now we're going to actually be using them to plot up data from a sedimentary nature. Interpreting some grain size data. And one thing I'm going to warn you is that when you first start doing research, there's a tendency to really kind of over-interpret things or under-interpret things. And what I find is that students are looking to find the answers to the big questions when they can't, and are missing some of the more subtle information that the grain size data can show you. Okay, so interpreting data, you've got to be a little bit careful about. And then lastly, we're going to be talking about some grain size parameters. This will introduce a little bit of mathematics to this course of statistics, because as we're always told, not a day goes by that someone doesn't come up to us and say, please sir, more math in geology. And we're very happy to accommodate this request. Let's talk about grain size. Grain size is a means by which to classify the particles that make up sediment into different components. And there are a lot of different schemes that are being used. Depending upon who you work for, you need to be aware of what those schemes are. Several of our students, most recently Michelle Johnson, worked for the U.S. Army Corps of Engineers. It's a very good group to work with. They do an awful lot of really good work, but they have their own way of doing grain size. They use something called the mesh size. The mesh size, in my humble opinion, is archaic. Nobody does that anymore except for the U.S. Army Corps of Engineers. Of course, if you work for them, you've got to get used to that whole idea of things. Soil scientists have their own scheme as well, and that one I've never fully understood or appreciated, so I don't do that. If you are a geography major doing soils, then you have to understand what their scheme is as well. Then we have what I collectively call the academic geologists. These are the people that would go in and do a research project, that would publish their results in a paper somewhere. So they're the ones that work for science. That's where we use a system that is based upon the metric system. This is the scheme we're going to be using. It's called the Uden-Wentworth grain size scheme. Now, you've already been introduced to this in Geology 111. At that time, we told you that we divide sediment up into 4 different components. Gravel, which was when particle size was greater than 2 millimeters. Sand, when the particle size was 0.063 to 2 millimeters. Silt, when the particle size was 0.004 millimeters to 0.063 millimeters, and clay anything less than 0.004 millimeters in size. By the way, it gets really, really, really annoying having to talk about decimal points. So geologists, who are among the laziest scientists on the planet, have come up with all sorts of shortcuts. Instead of using this, we just say it's 4 microns. That's 63 microns, etc. Okay, so microns is the equivalent of thousandth of a millimeter overall. This is the actual scheme here, and it's divided up into 2 components. All right, so this connects with that part through here, so you have to kind of put them together like this to get the whole thing. It shows you the actual size decreasing to the point where you can no longer see it easily, and then of course once you get down to silt size and clay sizes, you can't see particles at all. There's a taste test, which I'll be very happy to introduce you to when we're in the field, which can allow you to distinguish between silt and clay. But for the most part, when you get down to these levels, you have to do grain size analysis to determine the concentrations of them. When we introduced this to you in Geology 111, you know, nobody asked the question about why we had these really weird divisions. Now is a time for some history to explain why the boundary between silt and sand is at 0.063 millimeters and the boundary between clay and silt is at 4 microns. It has to do with the timing of when this scheme was initially proposed. Look at the date. This first was developed by Wentworth in 1922. Later on, Uden came in and modified a little bit later on. But the first reference to this is 1922. The 1920s to 1940s was an interesting time for science. Science had always been driven by European thinking up until the start of the 20th century. Then it kind of came over to North America. So a lot of things that we're now dealing with are North American based. But in the 1920s, let's face it, we didn't really know much about geology. This is, 20 years after Wegener first came up with the idea of continental drift, which was soundly rejected because nobody could figure out how it worked. All right, so we didn't have that understanding. We didn't know how mountains formed. We had only started realizing how old the Earth was in about the 1920s. So there wasn't a lot of science to our science, but there were lots of geologists running around. So what do the geologists have to do? Come up with means by which to classify everything. And a lot of the schemes you're going to see we use to this day are driven from about the 1920s and 1950s, because that was when they had to come up with some sort of technology or techniques by which to describe things. In the 1920s, they didn't really necessarily think in really simplistic fashion. Instead of coming up with numbers that would be nice and evenly spaced, they came up with this methodology of determining grain size. It's called the phi scale. Wentworth came up with the idea that we will base grain size divisions on this scale, which was based upon the negative log to the base 2 of the actual grain size. I'm not even trying to defend this. I haven't got a clue as to why this was done. They just did it. It's kind of like the same way as, when you look at how we name animals in the taxonometric binomial fashion, it's all done in Latin. The reason why is because the people who came up with that did it at a time when Latin was the language of science. If it would have been done in the 1900s, we would call a dog something that was a little bit more easy to remember, but instead we call it something based upon Latin terms. It's just the history behind this. Anyway, when you start playing around with the scale, these are what the divisions are. Everything is half of the previous division, but because of the negative component, the largest grain sizes are always negative phi. So if you start putting some simple math together, 16 millimeters represents 4 phi, 4 millimeters represents minus 4, minus 2 phi, 2 millimeters is 1 phi, 1 millimeter is 0, half a millimeter is plus 1, quarter of a millimeter. See the divisions? So the divisions in terms of where grain size falls between each of these boundaries in terms of things. It's done on the basis of phi. So if you look at the grain size divisions, they are even divisions on the phi scale, but as I said, very few people use phi anymore, so we have to go back to the whole metric equivalency to things and all. So that's where that comes from. As far as you're concerned, we're just going to use these divisions. And we're going to add a couple more. And this is done in a way that you can use visual ways to estimate grain size fairly easily. Gravel can be divided up into different components, but frankly, if you need to literally use a hand lens to identify something that's a boulder, and a boulder basically is like this big, then you've got some real serious issues. The real important divisions are down here in the sand divisions, because this is where you can learn an awful lot about energy regimes. Energy is simply the amount of movement possible of particles. Stands to reason that the bigger the particle, the more energy that you need to move it back and forth. There's lots of different types of energy. There's the energy associated with waves breaking on a beach. There's the energy associated with a river flowing down a valley. There's the energy associated with a landslide coming down an alluvial fan. So the size of the particles is determined, or at least that are deposited, is determined by the amount of energy that's around. It's in this division that the most subtle breakdown is required. Hence we have divisions for very coarse sand, medium sand, fine sand, and very fine sand before you get into silt and clays. Each one of these divisions is half of the previous one. All of them are easily identifiable in the field. All you need is a hand lens and some sort of a means by which to estimate grain size. Now, some of the things you can buy, and you can buy these things, allow you to do it by carrying this around. But remember I was telling you about nerdy geologists? You're walking around the field with this, your backpack and everything else. Yeah. you're going to be easily spotted. Eventually, you'll be able to put a little bit of sand on your hand, look at it, and tell whether it's medium sand or very coarse sand instantaneously. Until that time, I recommend what you use is get your tape measure out. Everybody's going to need a tape measure. I provide a good number of them, for groups anyway. Sprinkle a little bit of sand on the tape measure on the metric side of things. Look at it with your hand lens and mentally count how many grains put side to side it would take to fill up a millimeter. If it takes 2 grains to fill up a millimeter, that means it's half a millimeter in size, and your grain size would be coarse sand. That gives you a pretty good estimate of how grain size works in the field. But if you want to do it accurately, you have to have a more laboratory-based scheme, and that's what the grain size analysis component of this course is all about. I don't think I have to tell you that basically you go from the particulate material to the type of rock by simply modifying the name a little bit, okay? And you should also be aware that sandstone is basically a grouping of rocks that all contain sand-sized particles. There's a whole bunch of different sandstones, as you're going to see. A lot more than you ever learned in Geology 111, by the way. All right, so grain size classification. There's an issue. There's a problem. This is a recurring problem that we have in geology, and sometimes I think we're the only discipline that has this problem. We have got to deal with gravel, sand, silt, and clay. That's 4 variables. It's very difficult to classify in a visual way or graphic way 4 variables on a piece of paper, which is basically 2 dimensions. So we have a problem. The best way of solving this is to use ternary plots. And when I said that sometimes I think geologists are the only discipline that have this problem, it's based upon this. I don't know of any other discipline, with the exception of the geographers, that use ternary plots on a regular basis by which to represent data. I don't think the chemists even know what a ternary plot is. Sometimes the biologists do, after they talk to us about how to actually interpret the data. And the physicists, physicists don't deal with data at all. It's all up here type stuff, okay? But the ternary plot is classic in this situation, although we are still limited. Because ternary plots are designed to put on 3 variables onto a 2-dimensional piece of paper. We have 4, so we have to get tricky. We can only really deal with 3 variables at a time. The most common scheme that we use deals with sand, clay, and silt. You don't deal with the gravel component. And this is in part because most sediments don't have a significant gravel component to them. I don't know if that's true of every situation. Certainly if you get into braided rivers or alluvial fans, that's not true at all. But in the environments most likely you find this stuff in, you can literally exclude the gravel relatively easily. So under this scheme, what we do is we divide up a ternary plot where each corner is an apex of one of those grain sizes, and then we divide up the ternary plot into different fields. This is entirely empirical in nature. So in other words, if you plot up your data and it plots in this area here, you would classify this as little s, capital C, which if you look over here is sandy clay. Basically, the less important component is an adjective for the more dominant grain size that you actually have. Now this scheme was done by Folk in 1954. And again, it was done at a time when a lot of sedimentologists and geologists were busy classifying things rather than doing a lot of interpretations. This is one scheme that came out in 1954. This scheme came out the same year in a different journal about the same time. So at the time, geologists were sitting around trying to figure out how to classify things, and 2 completely different schemes came out at the same time. This is the one by Shepard. Now, to tell you the truth, this is the one I prefer. I use this one more often than I use Folk's scheme. And notice, and I have no say over this, the way Shepard proposed this was sand in this corner, silt in this corner, clay in that corner. So they're not exactly the same way around on this, okay? But this one is just the same type of thing. You analyze data, it plots up somewhere, and you use where it plots as a field to identify what the grain size ultimately is. Now these 2 schemes are the sand, silt, clay schemes that we use. There is a gravel scheme, and as far as I know, only one has ever been fully accepted. That's by Folk in 1954. So the same paper that he wrote this first one I showed you, he also said what to do in the event that you have gravel in here as well. What he did was he pulled out gravel, sand, and combined silt and clay to form the mud component. This is the type of chart that you would use if you were going to be looking at alluvial fans. I will tell you, when it comes to writing things up, if you ever wrote a paper or a report up on grain size analysis where you said, I did analysis and the sediment was largely clayey sand, then what you'd have to do in parentheses is put in Shepherd 1954 or Folk 1954, so whoever reads that paper knows which scheme you were actually using. It's one of the little things you have to deal with when you're dealing with reporting data. And there's little glitches like that in every subdiscipline of geology that you have, okay? If you're wondering, I mentioned that this is the one that I use most often, going back to the slide here. What do you do in the event that you have a little bit of gravel in one of your samples? Well, again, you know, schemes like this, if they're good schemes, and the reason why this one's been around for as long as it has is because it's easily modified. If the majority of my sediment plotted right here as a clayey sand and had a little bit of gravel in it, I would pull the gravel out of the analysis, analyze the remaining stuff, and then add a small g in front of this and make it a gravelly, clayey sand. All right? And again, it's intuitive. If someone reads that, they know exactly what I'm talking about. All right? All right, so let's talk about how to plot data. Now, how many of you have actually plotted ternary plots before? Okay, most of you would have done this. So for those of you who haven't done that before, however, let me just go over how this all works, okay? When you're dealing with data, where you are closest to the apex of each of these termini tells you how much of that particular material you have. So if you were to start off with a sediment that was 100% sand, it would plot right at the corner where the sand was. If you had a sample that was 100% clay, it would plot right up there. If you had a sample that was 100% silt, it would plot right down there. Each one of these things would be named according to whatever the field it fell in. So this would be Z for silt, this would be C for clay, and this would be S for sand. The complications occur when you don't have 100% of one grain size. If you have two variables, then you will have them plot directly on the line between them. This particular sample here plots at 50% sand and 50% clay. 50 plus 50 equals 100%. That's where the 50% clay and sand would plot. That's where 50% clay and silt would plot. And lastly, that's where 50% silt and sand would plot along the edges. We refer to this part as the sand triangle, at least I do. The sand triangle shows you where sand is the dominant component. And the way it works is, you start here and the line opposite, or the side opposite, is the zero line. If that's 100%, that's zero. There's the line that represents 50% sand. So everything above this point has more than 50% sand in it. 50, 60, 70, 80, 90, 100% sand. The clay triangle is tilted 120 degrees from that. There's 100% clay, there's 50% clay, there's 0% clay. 60%, 70, 80, 90, 100% clay. Notice that one side of the triangle shows you the percentages of the line going towards this corner. These numbers show you the percentages going off in that direction. Okay? And then lastly, of course, there would be the silt triangle, which is tilted the opposite direction. Now to plot data, and this is, I'm going to give you an example to do a little bit later on how to plot this data, because it's kind of fun to do this. You need to have your numbers come up to 100%. That's the trick on this. For any ternary plot, the numbers have to add up to 100%. In this case, we have a sample that's got 46% sand in it, 25% clay in it, and 29% silt. Everybody has their own way of doing this, but the way I do it might work for you if you haven't done this previously. I would argue that if that's 100% sand, and that's 90, 80, 70, 60, 50, and 40, then a sample that has 46% sand would plot on a line somewhere along there. I don't know where along the line it would, but somewhere along here it's going to plot. So let's put a line there that represents 46% sand. Now you could go in any direction you wanted. You could either do the silt one or the clay one. I chose the next one to do, I believe, is going to be the clay line. And clay has 25% clay. Well, if that's 100% clay there, and that's 0% clay, well, there's 10, 20, 30. So 25% must lie somewhere in that general area like so. And indeed, that's where the line would go. Now, it stands to reason that the point it's going to plot is going to be at the place where those two lines cross. But you should still do the third one anyway, because sometimes you make a mistake. If you do this and you plot all three of them and they don't overlap in one place, one of those lines is wrong. So let's make sure the third one plots in the same spot. 29% silt. There's 100% silt. There's 0% silt. 10, 20, that's about 30% there, right? So along that direction, they all plot the same point, and that is the place where your point would plot. That means that sample would be classified as a sandy mud under the Folk 1954 scheme. All right? Now this is a good way of dealing with data. It's a good way of classifying data of a grain size nature as well. What it doesn't do, though, is distinguish between a sample that plots here and a sample that plots here, because those are both sandy muds. But one that plots down here has more clay in it than one that plots up in this direction. So usually, it's instructive, if you've got 10 samples that you have done, to plot all of them up on the same ternary plot. Often you'll find you have them arranged in a line like this, which shows you that from one sample to another, there is gradually increasing sand and silt, or if you wish, a reduction in clay. So simply putting the data up here for data's sake isn't allowing you to get all the information that you could get out of grain size analysis, because you may be seeing a trend of gradual coarsening or gradual reduction in sediment. And that's an important thing to consider as well. Okay? Now, does anybody have any questions about ternary plots? As I said, I'll give you an example to do in one of the assignments a little bit later on. It's not hard stuff. It's just kind of, it takes a little bit of time to do it and all. Now, there's another way that you can represent data for grain size through standard histograms. And incidentally, the spreadsheet I'm going to give you to do your grain size analysis will automatically plot things up in the ternary plot for you. It will automatically spit out these things for you as well. But now comes the ability to interpret things. What you're looking at here now is a standard way that we represent grain size in histogram fashion. On this axis is percentage. On this axis is grain size. For this methodology, it's always coarsest in this direction, getting progressively finer in this direction. You're going to see a little bit later on. Unfortunately, we have a tendency to be inconsistent when dealing with grain size. When we start talking a little bit more about how stuff works, it's flipped around. So just be careful and make sure you know which one is which. For this type of histogram, coarsest here, finer in that direction. So what you're looking at now is a sample that consists of a good chunk of coarse silt, a bigger chunk of fine silt, and a larger chunk of clay. In other words, a sediment that is dominated by the finer sizes of sediment. Often you'll see people doing it in histogram fashion, or you'll also see curves that look like this. The curves more or less just join the points of where the histograms would be, and they take the histograms off. Sometimes people read the curves as being better. Or easier to read. But here we have a rock or sediment that is composed dominantly of fine-grained sediment. There's some information you can gather from this or interpret from it, but you also have to be a little bit careful about how far you go. So the question I have for this, and I open this up to anybody who's in here now, what kind of depositional energy was associated with this sediment? Very good. Because last year, when I asked that very question, everybody said floodplain. Why is low energy correct and floodplain wrong?
You see larger sediments in the floodplain.
No. What is a floodplain? An environment. Can you tell what environment this is based upon grain size. Now it's true. A floodplain normally is characterized by fine-grained sediment. But the fact that it's fine-grained sediment does not make it interpretable as a floodplain, because this could have been an estuary, this could have been the toe of an alluvial fan, this could have been anything. The information you can gather from data like this is that whatever was going on, it was relatively low energy in origin because there's no coarse grain material here whatsoever. The fine-grained stuff would have been deposited in a place where there were virtually no currents whatsoever. But that could be any depositional environment where those conditions exist. All right? So well read. All you can say is that this is a low-energy environment. How about this one? Now what we see is a tiny amount of gravel. That's probably a mistake, by the way. Maybe a little plant material got caught up in the situation. Notice that there is a peak, almost Gaussian in nature, centered around fine sand, with a tail of silt and clay on it, but not much else. It's a moderately sorted sediment sample. In other words, that it tends to be kind of focused in the middle, but there are tails on either end. What do you think in terms of depositional energy? High or low? Or medium? Yeah, medium, lowish. It's hard to tell exactly what it is, but I will say this. Whatever the energy was, it was fairly consistent. If it was all over the place, if it was coarse sometimes, if it was like highly energetic sometimes, not so energetic other times, it might be mixed up. You might expect to see a curve that went more like this. It still was kind of moderately sorted, so whatever the energy was, it was sufficient to move sand around and to keep it relatively well sorted. Okay? How about this one?
Intermittent.
More accurate than you probably even realize yourself.
Well, I mean, you've got fine-grained stuff, so you've got a low-energy environment, but periodically you've got an event happening that just
Excellent.
down there.
Excellent. Now, one of two things has happened. Either the person who sampled this wasn't thinking very clearly and took two layers together, or the actual sample he had might have had a mixture of two different populations. Something like that. Now, in situations like this, now you can start thinking a little bit more about the depositional environments that are there, especially if we're talking about stuff that is interlayered very thin. All we could say for the depositional energy of this is it's mixed. But if this is consistent, now we have two populations that overlap. One relatively well-sorted fine grain, one relatively well-sorted coarse grain. So what kind of environment can you think of where you're going to have the idea is it isn't where you had intermittent, like once in a while. If you get this type of distribution, it usually means that for part of the time the energy is one situation, part of the time the energy is something else. What kind of environments can you imagine that change frequently or intermittently, as you say?
Point bar.
So,
Point bar.
possibly point bar? A tidal flat? It does start to narrow things down significantly. It's not an estuary. I would argue it's even not a point bar. I think point bars are more consistent than all that. But it's going to be maybe a floodplain, close to where a river was. You're starting to really reduce the number of possible environments it could be. And in some situations, you can get enough information from the grain size distribution to be able to say, not only is this a high energy environment, but it had to be a high energy environment on a tidal flat because that's the only place something like this happens. Those are rare, but they do occur from time to time. All right, now let's talk about mathematics. See, no one has groaned. I think it was a chair that made a noise, right? As with all aspects of geology, there's different ways you can go with, all aspects of science, there's different ways you can go with stuff. If you're in physics, then your life is largely based upon stats and mathematics. Same is true with chemistry. Biologists try to get away with it as much as possible. Geographers don't know how math works at all, but geologists do occasionally have to do this from time to time. And again, a lot of these names that you can see, there's Spoke's name again, Inman, Trask, these are all things that were proposed back in the 1950s, 1940s to put some quantification to the data that we're dealing with on a regular basis. Now what you're looking at here are methodologies for measuring the median, mean, sorting, skewness, kurtosis. There are 3 different methods that are used. If you are using a store-bought grain size analysis package that uses a different type of technique than what we're going to be doing in our grain size here, then they normally give you the stats for each of these. You just choose which one you want to use. Most of us tend to prefer Folk and Ward, and that's the one that I'm going to talk about here in a little bit more detail over, okay? It's all based upon stats. When you do your grain size analysis, you'll be able to put all your data into a curve that looks something like this. And you should recognize this as a standard Gaussian curve dealing with things like significant or standard deviation, etc. That we're not going to be talking too much about this, except to note that when you're looking at something like this, you're going to see percentile components to this, and these percentile here are going to be what is used for determining the actual grain size parameters we just talked about. Now, focusing on the Folk and Ward side here, and only the Folk and Ward side, these are the important ones that you need to be aware of, okay? First of all is the median. The median is defined more or less as the 50 percentile component of things. This is where you would end up having the grain size that falls right at the 50% component of things, okay? The mean is the average. Now, when you do an average, you add up all the numbers and divide by whatever numbers there are. When you're dealing with grain size analysis, the mean is determined based upon the 16th percentile plus the median plus the 84th percentile, all divided by 3, okay? Sorting is one of these things that is really kind of, well, you'll see in a second, sometimes it's better to use a visual approximation than just numbers. Sorting can be done mathematically by looking at these percentile in this relationship, but as you'll see in a second, there's another way you can do sorting. The mode, most frequently occurring particle size, is equivalent ultimately to the median, but you see the mode used separately as well. And if you're wondering why I'm going through this so fast, it's because I don't do this stuff, and you don't have to do it here either. I'm just giving you what's done from the statistics side of things. Skewness is interesting. This is one of those parameters that allows you to determine the shape of the curve. Okay, so there's the mathematics behind all it works. But the skewness can also be defined in the following way. Anything that's got a shape like this to it is said to be positively skewed. Some people say it's finely skewed. Anything that has a shape like this is negatively skewed, or coarsely skewed, or symmetrical. Okay, so the skewness is interesting because it tells you something about the particle shape. Now remember, you're going from coarse grain to fine grained, okay? So a curve that's got this type of shape to it tends to have fine grains dominating with some coarse grains around it. This one tends to have very few coarse grains given the number of fine grains that you have. This is often taken as a sign of a winnowing phenomenon. Winnowing is where you have sediments been deposited, and then something happens later on. Say the currents pick up a little bit, all the fine grained materials are preferentially washed away, leaving coarser grained material behind. So this tells you something about maybe a secondary process affecting the sediments. This one has often been taken as a sign of diagenesis. Suppose you have a Arkose sandstone, a very well sorted Arkose. But Arkose consists of an awful lot of feldspar particles. Feldspars are unstable. Feldspars can break down within the environment that they were deposited as grains, giving you kaolinite. And what's kaolinite but a clay particle? Net result is all the feldspar breaks up to clays, leaving behind some sand grains, leftover quartz, and everything else turns into a fine-grained sediment. And you're wondering, how in God's name could you have very few coarse grains but a lot of fine-grained stuff in a deposit? Well, sometimes it's because it wasn't the deposit that caused it, it were events that occurred afterwards. That, incidentally, really needs to have secondary petrographic analysis to confirm that idea. Kurtosis. Unfortunately, none of you have ever had the chance to talk to Wayne Ishfording, have you? Has anybody ever met Wayne? He he was here up until about 2008 when we hired Jim Connors on to replace him. So however long Jim's been here as a teacher is when Wayne has not been here. Wayne used to be our expert in everything, and he was an expert virtually everything he got involved with, and he did a lot of grain size analysis. And when I first came here 20 years ago, my God, it's a long time ago, I went up to him once because I was the sedimentologist, and I was trying to figure out what kurtosis was used for. Kurtosis is described as the shape of the peak of the curve, of the grain size curve. And I went up to him and I said to him one day, I said, Wayne, what do you use kurtosis for? Because he did a lot more grain size than I did up in the time. And he said, I haven't got a clue. I said, so why do we do it? He said, just because. And he walked away. And I thought, okay. And I said at that point, if Wayne Ishfording doesn't know what kurtosis is used for, then I don't think we have to worry about it at all. But I will say this, it is linked to the sorting. So the closer you are to a peak that looks like this, the better sorting something is. So if you have a curve that looks like this, whatever the energy was, it was consistent within a very narrow range. If it looks something more like that, it means that the energy was not really all that consistent. That's probably the best way of describing what the usefulness of kurtosis is. Now, all those properties I've showed you are really only useful if you want to know the mathematics behind grain size distribution. You'll be very happy to know, or perhaps not, that the methodology that we're going to be using for grain size analysis in this class does not spread out numbers like that. It is not done on the basis of statistics. It's done on the basis of physical sampling. There's pros and cons to doing that methodology. I'll tell you all about them when we start doing this in the laboratory later on. There's a couple other descriptive parameters I want you to be aware of. They include roundness and particle shape. Now those two things are different, okay? The roundness of a particle basically talks about its angularity. That's a fairly angular particle. That's a well-rounded particle. But this versus this is particle shape. A well-rounded square grain looks like that. A well-rounded rectangular grain looks like this. Okay, so these are two different properties you have to be aware of. Now, both of these properties can be qualitatively and quantitatively determined. The quantitative methods are a pain in the butt, like you would not believe. The qualitative methods can be done on the fly. Let's talk about particle roundness to give you an idea how this all works, okay? This is the quantitative methodology. And I'm going to talk you through how this all works and then explain to you how I had a personal insight not in how this was done, but I was kind of contracted to look at roundness of particles and I had to make a decision which method I wanted to use. To do the quantitative method, what you do is you take a grain like this. This would be the actual shape of the grain. Usually what would be done is you would literally, in the old school, I guess you can do it with computers now, but in the old school, you would put a grain on an overhead projector, enlarge the shape of it, draw it on a piece of white paper, exactly going over the edges on it. Then what you would do is you would attempt to draw the entire surface using a series of circles. The idea was that every part of the surface had to be designated by part of a circle or more circles. Stands to reason, the more asymmetric or the more angular the grain, the more smaller circles you'd have to have. Had to be one and through here, etc. Then you count the number of circles. The more circles you have to designate the shape, the roundness of a grain, the less round it was. Okay? But here's the trick. In order to make it statistically significant, you have to have a minimum number. And in geology, that's 300 grains. You would have to randomly choose 300 grains, project every single one of them onto a screen, do the circle thing entirely for each one of them, and then average out all 300 grains to give you a number. Several years ago, when a group was trying to figure out how to replenish sand on Dolphin Island, they contacted some sedimentologists in the area, and they contracted different components to each of them, saying, could you do this for us? We're trying to figure out if the sand, we found this great source of sand, it'd be a lot cheaper to truck it in by dump truck than sucking it off the Gulf bottom and piping it over here and filling this gap. So we could probably replace all the sand off Dolphin Island in no time flat. But we need to make sure that the sand that we're going to be putting on here is exactly like the sand that we're dealing with on Dolphin Island today. So somebody got grain size and they asked me to do roundness. And then these were engineers, so I know how engineers think. I said, so do you want it qualitative or quantitative? And they said, well, we always like ours to be quantitative. They like numbers. Engineers like numbers. And I said, okay, well, before you say this, you should know that this is what I have to do. And I said, I'd have to do this 300, etc. And I said, my services will cost you $250 an hour. And I figured it'd probably be about, what, 10,000 hours doing that? Then they said, how much will the qualitative stuff work? And I said, well, you know, significantly less, because here's how qualitative would work. You take a grain, and you compare it to this chart. And you say, that one. That gets a 0.4. You still have to do it 300 times. But how long does that take? It's qualitative because there isn't a number. Now, I can give you a number because you just average up all these numbers and put a number on it. But the fact of the matter is, that's probably as useful for what they had to do for the project that was involved, okay? By the way, if you're wondering about how all that worked, this is what my data was all about, okay, in terms of the grain size differences and all this. It was not too bad overall. That project never went ahead because while my stuff confirmed that the roundness was okay, someone else that was doing the color, that must have been a pretty good one. They had a Munsell color chart. They took sand from Dolphin Island, put it on the chart and said, creamy yellow. Took their sand, slightly red. That was it. So the whole project was shut down because they couldn't match the colors. Don't you love science? So, descriptive parameters, qualitative fashion, are useful. Get familiar with the idea of being able to do grain size on the fly by using a tape measure and your hand lens, recognizing the difference between coarse grain sand and very fine sand, etc. Get an idea for describing the roundness. Something like this can be angular. Something like this is well-rounded. If you don't want to use it just in terms of a descriptive fashion like that, there is a chart and one of your sets of notes. Feel free to put a number down instead. But these are the types of information that you need to record when you're in the field. As far as sorting goes, yeah, you can use the mathematics. Or again, you can look at something and get an idea between the difference between something that is poorly sorted, where there's grain sizes of completely different size all in one sample, versus samples where the grains are all more or less the same size. Now in hand specimen, this is easy to do. You put a little bit of sample in your hand and you look at it. Be careful with thin sections, because when you do thin section, you're slicing a very thin layer through a rock sample. And remember, rocks are three-dimensional. If you have grains that are all the same size, if you slice a grain through the middle, it will give you a circular cross-section like this. But if you take a grain that's the same size that happens to be a little bit lower down than where the plane of the thin section was, you skim the top off, you get a small grain. That does not mean poorly sorted. It just means that you've sliced grains through at different directions, okay? So identifying sorting in thin section is a little bit more challenging than doing it in hand specimen. Now, as far as sampling techniques go, and this is something that you will learn as you become sedimentologists, and I'll try to give you as much experience with in this class, you have to be able to deal with unconsolidated soft sediment, which is what we normally have around here, or lithified sedimentary rocks. So if you happen to be going up north where there are Paleozoic limestones, then bringing one of these things along is going to be good for swatting the flies, but you're not going to make much inroads to the rocks, which are friggin' hard. Bring a sledgehammer when you're up there, okay? Unconsolidated sediments down here, depending on how and what you're doing, you might be able to get away with a grab sampler. A grab sampler is deployed usually from a boat. If you're looking at sediments that are below water, you drop it down. When it hits the bottom, it scoops up, you pull it back up, and you get your sediment from the top. This usually gives you a semi-disrupted sample from the top 15 centimeters or so. When I say semi-disrupted, when it closes, it normally takes the sediment and squishes it. Some grab samplers, incidentally, will allow you to take an undisturbed sample. You can core it, and we do have this option available to anybody or any group that wants to take a core sample from, say, the middle of the lake in Municipal Park. It's a little bit more challenging. Probably need 2 kayaks. Someone's going to get wet. always happens, but you can extract a complete core that will go down for the length of time that municipal park has been in operation, which is what I think about 100 years. Now, Mary has been doing some direct research with me, and last week she and I had a fairly successful session in Weeks Bay. In really windy conditions, we managed to get 4 cores that were collected. And what was the thickest we got? 5 cores, sorry. About maybe 4 feet a core? There were 5 feet barrels, so I think one of them was pretty full. And basically, a piston core allows you to extract sample through soft sediment. Now, you're not going to get that type of recovery in municipal park because it's probably only got about that much sediment since the thing is opened up. But you'd be surprised on what you can try and get if you want to give it a go. And of course, hand sampling. For those of you that decide that you'd rather do a project that was on land, bring a little shovel with you, or I'll lend this to you. It cost me $35, so I'm going to have to charge you rent on this, maybe like 10 cents a stroke or something. Lithified sedimentary rocks, a hammer works well, a sledgehammer works well, but you know what? If you're going to be cool as a sedimentologist, the best thing to have is one of those diamond drill coring things. They use a chainsaw motor, and they've got a diamond barrel on it. They're lightweight. You take them to the rocks, drill a hole through it, pop it out, you got yourself a little column of rock. I want to get one of those things. Or you can get a saw that's also chainsaw based. It's a diamond saw. They are also cool. You can extract samples out that way as well. Hammer's cheaper. All right, now with that being done, we're done with the first 2 lectures of this course. Thursday, we are not meeting here. Thursday, I would like you to meet me at the amphitheater, you know, the band shell at Municipal Park. Be there around 11:15, okay? Get there earlier if you can, all right? But get there 11:15, no later than that. I will be leaving campus at 11 o'clock in a van. I will try to get a second van for Rachel if necessary. If you want a ride, email me and I'll add you to the list. If we have more requests for a ride than we have space available, I might contact people who are planning on driving on their own anyway and get them taking more people with them. We will be back here on campus no later than probably about 1:30. Give you plenty of time to get yourself all sorted out. All we're doing on Thursday is a walk around Municipal Park. I'm going to talk to you about some of the potential ideas that are available there, but not give you specific projects to do. That is for you to decide. What I'd like you to ultimately do is to either come up with a project on your own or to work with a group of 1 other person or 3 other people to come up with a project. So the permittable numbers of students are 1, 2, or 4. I don't want to see any groups of 3 because they end up being all sorts of problems for running the grain size labs component. That's where we're going to get bogged down, is using the grain size analysis equipment. All right, and that's going to cause things to be dragged out significantly. Now, in addition to that, your first writing assignment, and this is indicated in that package of stuff I gave you as Write 1, is due Thursday. All of you have taken a W course before. All of you probably know what a paper should consist of and how each paper should be broken up into different components. For example, all of you know that scientific paper will have an abstract, an introduction, background, methodology, results, discussion, and conclusion. I would like you to write up, very short, usually 1 page is sufficient for these writing assignments, what you believe to be the difference between the abstracts, introduction, and conclusion sections of a paper. Feel free to consult other sources. Beware, Wikipedia is offline tomorrow, so don't rely on Wikipedia, at least tomorrow. In fact, use Wikipedia and other sources like that to give you some ideas for this, but remember, we're science. So make sure you're focusing on the scientific ideas. In the past, people have looked at that, and what it is basically someone wrote it up in terms of what you would write up if you were in an art history class. Okay? When you have a chance, since you're going to be doing grain size analysis, I would recommend that you read the lab manual or the grain size manual. It's online. It's also included at the back of the blue section in the package of stuff I gave you. This weekend, if I were you, I would plan on getting my samples Because the sooner you get your samples, the sooner you're into the system for doing grain size analysis. Now the rules are as follows. Actually, I don't know what the rules are. I think it's 5 samples per person. Yeah, I think it's 5 samples per person. So a group of 2 would have 10 samples. A group of 4 would have 20 samples. All right, you cannot cut back on the samples for the number of people you have in the group. You just work together in analyzing all the stuff and interpreting and writing it up. And remember, if you're working in a group project, you will be marked as a single grade for all the people in that group for the final project. You're still going to be marked independently on your writing, sub-writing components and stuff, okay? And next Tuesday when we meet, we're going to get into sedimentary rock classification, okay? So no lecture on Thursday. We will meet at Municipal Park, and I hope the weather's going to be okay. It's supposed to rain pretty bad today, but tomorrow and Thursday hopefully be okay. I have to warn you, I'm having less good luck with the weather. It used to be Allison got all the rainy days, but it's been me lately. So bring a raincoat if you need to, right? An umbrella. All right. Catch you later, folks. Lights coming on.
Hey, Doc.
Yeah. Sorry, what? Oh, the band shell.